Welcome back to our energy unit. We are in lesson 6 today, and we are talking about waves. Now, waves are not a form of energy. So you might be asking yourself, what in the world are we talking about waves for if we're moving through the different forms of energies? Well, one of the forms of energies that we learned about in lesson 1 is electromagnetic energy. And so electromagnetic energy is going to come into play, but we need to know a little bit about waves, because one of the things we're going to learn when we start to dig into waves is there are two types of waves, and one of those types of waves is electromagnetic waves. So we've got to do some background work before we jump into the form of energy, but waves definitely do relate to forms of energy, even though waves itself is not an actual form. So there are many different ways that we see waves in our everyday life. Some are obvious, like water waves. And then some, like light waves, we just sort of don't really notice. We just notice maybe the effects of those waves. By definition, a wave is a repeating disturbance or movement that transfers energy through matter or space if we're talking about electromagnetic waves. So we're going to go through and talk about the different types of waves, some examples, and just kind of get some background information before we jump into how waves relate to energy. If you'll answer this question for me, hopefully you remember a time where you dropped something in a puddle of water or bucket of water. So if I were to drop a pebble into a puddle of water, what would you notice? And hopefully you remember from past experience that you probably notice ripples in the water. That's because the pebble or whatever you drop into the water has energy. And remember, law of conservation of energy says energy is not created or destroyed, but it can transfer. So the pebble transfers its energy to the water molecules of the pond or the bucket or wherever the water is, and that energy moves out into the water molecules. And so we see this as a ripple effect. So the matter through which a wave travels, for example, in the last picture, we saw that the energy traveled through water. So whatever the matter is that the wave has to travel through to get to wherever it's going is known as the medium. So be sure that this vocabulary term gets put in your notes. So a medium is the material or matter through which a wave travels. Mediums can be gases, liquids, or solids. And it's important to note that all waves carry energy, but they do so without actually transporting the matter in the medium. So a good example of this is if you've ever been fishing in a boat. A boat could be anchored and it can just kind of bob up and down, and the waves can be moving under it. And this is a great example of how energy moves through the water in the ocean or the lake or the pond, but it doesn't carry the matter in the medium with it. So you can see that in a couple of these pictures here. The energy moves, but the matter of the medium doesn't move with the energy. Now, a wave will only travel as long as it has energy to carry it. And a good example of this is if I were to drop a pebble in a puddle of water, I would see those ripples, but they don't last forever. Eventually, they dissipate. And so the energy will soon transfer into different places and the energy will die out. Not really, though, it just transfers to a different location. So anything that moves up and down or back and forth in a rhythmic way is said to be vibrating. And vibrations are the source of waves. So waves start with a disturbance or a vibration that moves energy through the matter or through a medium. So there's two main types of waves. We have what's called mechanical waves and then electromagnetic waves. And this is where our energy comes in, or forms of energy comes in. So let's look at mechanical waves first. These are waves that can travel only through matter. So mechanical waves have to have a medium to travel through. That could be a solid, a liquid, or a gas, but it has to have a medium through which to travel. So some examples of mechanical waves are like sound waves. So right now you can hear my voice because sound waves are moving to your ear. Ocean waves, we've talked about, even the stadium waves. So if you've ever been to a ball game and there was a massive stadium wave, this is an example of a mechanical wave. So the actual energy moves through matter. So all of these waves must have a medium to get to where they're going. So again, sound waves have to travel through air. Ocean waves, the energy travels through water. The stadium wave, the energy travels through the people, etc. So mechanical waves have to have a medium. And so that brings me to this question. Are there sounds in space? So we're talking about in the vastness of space where there's no air molecules, is there sound? So I'm going to let you think about that question for a little bit, and when we come back to electromagnetic waves, I will answer that question for you and give you more detail into why there is not sound in space. So before we get there, let's talk about the two types of mechanical waves. So remember, we have two types of waves, mechanical and electromagnetic. We're focusing on mechanical waves, but we can break this down further. So mechanical waves can be further subdivided into two different kinds. We have compressional, or sometimes this is referred to as longitudinal waves. You will see me refer to both of these. So just make sure you understand compressional and longitudinal waves are interchangeable. Then you can also have transverse waves. All right, so let's start with transverse waves. In a transverse wave, the wave is going to travel side to side. So the energy is going to move left to right or right to left. The energy is going to travel side to side, but the actual matter in the medium is going to move up and down. So let's look at this wave. If you just kind of look at the wave as a whole, you'll notice that the energy starts on one side of the screen, and you can see that energy move through in sort of a rippled way all the way across the screen. So the energy moves from left to right. But if you focus on any one dot in the picture, you notice that the dots are just simply moving up and down. And so this is what I want you to know about transverse waves. The energy moves from side to side, from one side of the wave to the other. But if you focus on the matter inside of the medium, it's just going to move up and down. Okay? So this is why a boat that's on water that's anchored down will just kind of bob up and down, because the energy is moving through the water, which is the medium, but it's not carrying the actual matter with it. So in a transverse wave, the matter in the medium will always move perpendicular to the motion of the wave. And again, this is a transverse wave. Here's another example or another animation. So you can see the energy is moving from one side of the screen to the other, but the actual matter in the medium is just moving up and down, up and down. Now, in a compressional wave or a longitudinal wave, the energy is going to move side to side. So if you look at this animation, just kind of look at it from afar, you'll notice that it looks very similar to a conveyor belt. The energy is moving across the screen from left to right. But the difference is the actual matter. So if you focus on any one particle of matter in the picture, you'll notice that it's not moving up and down like in transverse waves. It's moving side to side, side to side. So that's the difference between a compressional wave and a transverse wave. Examples of compressional waves or longitudinal waves are slinkies. Like if you were to take the slinky and just kind of press it together and release it, that's a good example. let me go back here. You also need to, we're going to talk about different parts of compressional waves and different parts of transverse waves in another lesson. But here you can see in the picture of the slinky, in a compressional wave, the areas that are compressed or kind of squeezed together are called compressions. And then rarefactions are the parts of the wave that are just kind of spaced out or spread out. Electricity is another example of compressional or longitudinal waves. All right, so take a look at this picture. Would you say this is transverse or a compressional wave? So we can see the wave is moving up and down, the energy is moving up and down, and hopefully you said this is a transverse wave. All right, in our next example, this is just sort of an example of how sound travels. So you can see here, the energy is going to move from that circle and project outward, but the matter in the medium is just going to move side to side. So this would be an example of a compressional or longitudinal wave. All right, so here's a picture here that's representative of brain waves. So you can see the up and down motion of the wave. So hopefully you could identify that as transverse. Right here we have the sound from a speaker move into a receptor or a person's ear. We can see areas of compressions and areas of rarefactions. So this would be an example of a compressional or longitudinal wave. Again, compressional and longitudinal are interchangeable. They mean the same thing. All right, so let's look at some different properties of waves. So all waves are different. We've already seen this with transverse waves and compressional waves, and it's going to become even more apparent when we get to electromagnetic waves. You can have different sizes of waves. They can produce in sound. They can produce different types of sound. You can have waves that are far apart or they have a greater wavelength versus a shorter wavelength. You can have different frequencies, but all transverse waves have similar shapes. So we've seen this already. All transverse waves have sort of that up and down shape, no matter how big or small they are, no matter how short or long their wavelength is. So the very highest point of a transverse wave is known as the crest. The very lowest point is known as the trough. You also need to be able to identify the amplitude of a transverse wave. So the greatest distance that all the particles are displaced from their resting place on a wave is called the amplitude. So if you'll look at this transverse wave, there is a horizontal line that runs smack dab through the middle. That's known as the resting point. And so the height of the wave from that resting point to the crest or from the resting point to the trough would be the amplitude of the wave. And we're going to learn with sound waves, the amplitude has to do with loudness of the wave. Larger waves are going to have bigger amplitudes, and this is because they carry more energy. Now, compressional waves or longitudinal waves have different areas as well, but they don't have crests and troughs. They're going to have compressions and rarefactions. So we've already discussed that, but just make sure that you get it in your notes. Compressions are going to be the areas that are more dense or condensed, and rarefactions are going to be the spots in the wave that are more spread out. Now, wavelength is something that you need to be familiar with in a wave. So in a transverse wave, wavelength is going to be the distance from the crest of one wave to the very next crest of the next wave. So from crest to crest, or you can measure wavelength from trough to trough, or from the middle of one wave to the middle of the very next wave. So a lot of different ways you can measure wavelength, but it's always going to be one point on a wave to that same point on the very next wave. Now, frequency is a definition that we need to make sure that we get in our notes. The frequency of a wave is going to be the number of wavelengths that pass a point in a given time interval. So you can have high frequency, which means lots of waves passing through a point in a given amount of time, or low frequency, where you will not have as many waves passing through a point in a given amount of time. The symbol for frequency is this italicized F, and the unit for frequency is the hertz. All right, that completes this particular lesson on waves, and I will see you in the next lesson.